diagram or a Ramachandran plot if you are unfamiliar. Okay, this is an energy map of shown as a function of phi and psi angles. Okay, so it was originally described in 1963 by someone named Ramachandran. Surprise, surprise. In the supplemental resources, the seminal paper that describes this plot and shows the first one is given. If you are interested, it's again a short paper if you're interested in that reading. Okay, so here we have our phi angle, we have our psi angle, and again, he said something like, oh, 0, 0 is a forbidden spot, okay? So there's nothing on the plot here, there's all this empty space, okay? And all of these individual dots here, or what is now sort of kind of a rough outline of possible like phi and psi combinations. How this was basically done is looking at a bunch of proteins, okay? Analyzing a whole bunch of proteins and figuring out in an alpha helix what were the phi and psi angle, right? Looking at a bunch of beta sheets, what were the phi and psi angles of those atoms that were participating in a beta sheet? And so what was essentially assembled is regions of angles that alpha helices will most likely form, beta sheets will most likely form. This is left-handed helices, okay? And everything in white is combinations of angles that cannot happen through literal steric repulsion, or atoms can't occupy the same physical space. So those are impossible. So Ramachandran looked at an alanine-alanine dipeptide to sort of start assembling his diagram. Why alanine-alanine? Why not glycine? And the structures are sort of up here. Sure. Okay, glycine is not chiral. That is true. Other special things about glycine? Right. Perfect. So glycine is super flexible. It just has this tiny h, okay? And so glycine is actually a little bit more flexible in what angles it could possibly be in, okay? Alanine is the next smallest side group. It just has a methyl side group instead of just an H. If there's a spot where two alanines would be clashing, anything bigger is definitely going to be clashing, okay? So alanine represents, you know, if that's a forbidden combination of angles for the smallest like the smallest side group that isn't just H, everything else would clash there too. What might this be the plot for? Sure. Glycine, beautiful. It's less restricted, and so glycine residues tend to be able to kind of be in some of the forbidden regions or anywhere. Here's sort of a more souped up looking plot based on energetics. So again, low energy is what we're looking for, okay? Everything wants to be in the lowest possible energy state, so this is again kind of showing you combinations of angles where alpha helices will generally form, beta sheets would generally form, and then these spots that are really, really high energy represent it's impossible to be in those forms. So most combinations are, in fact, disallowed due to atomic collision. This is myoglobin. Okay, we said myoglobin is just a bunch of alpha helices. So if you actually take this alpha helix here and look at just one stretch of it, okay, and look at the phi and psi angles between this stretch of like six combinations, and then plot what the actual angles are in myoglobin, you'll see that all of those actually fall in the alpha helix region, so you're not surprised to find them in an alpha helix. I forget which protein this is. It might be one of the SH domains, actually. And again, when you isolate just a stretch of one of part of the beta sheet and just look at one stretch of the backbone and look at the phi and psi angles, you'll see they all fall in the beta sheet range. When you have loop segments, connecting segments, or you're looking at the stretch of the protein that's sort of unstructured, it might fall in the beta sheet, it might fall in the alpha helice range. It's important to know that when you're seeing like sort of a mixture everywhere, you might be looking at a loop, hairpin, unstructured part.